Okay, so this video covers least squares regression. We're going to talk about how to interpret slope and y-intercept of a least squared regression line. We're going to use the LSRL to predict y given an x. We're going to calculate and interpret residuals. We're going to explain what is meant by the least squares, and then we're going to determine the equation for the LSRL. In no particular order, mind you. So first, a regression line. So we know what a scatter plot is now. A regression line is a line that describes how a response variable y changes as an explanatory variable x changes. And it's used to predict a y, right? It's not going to say that the y values that you have are on the line, but if you have another if you have another x value that you are anticipating, then this gives you a way to predict what y value you'll get as a response. It's a nice, convenient way to summarize the relationship between two variables. We know that R describes the strength and the direction, but it doesn't give us a whole lot else. Linear relationships used to. It's something that's easy for us to understand because of all the math that we have as our background. So LSRLs basically allow us to take something familiar and use it to describe something that is not easy to describe. When you're interpreting a regression line, you're going to have a few things to look at, right? So it models the data just like density curves model the histograms, right? It's not going to be precise. It's a model. It gives us something, like I said before, it gives us something to use to predict future results, future outcomes. Regression line has a form y hat equals a plus b. It is pronounced, it is said y hat. It is the predicted value of the response variable for y given a certain value for x. B is the slope. It measures the change or describes the change of y with respect to x. And then A is the y-intercept. It tells you basically what y would be if x was 0. It's sort of like the starting point that we had back in algebra, right? An example that we have here, we have price equals 38,257 minus 0.1629 miles driven. So what that tells me is that if I'm trying to predict a price for whatever the scenario is, I should start from, if my x is 0, I would be starting with a price of $38,257. And then as I increase the number of miles, for every mile I increase, I decrease the price by this much, right? And that is modeled here on this line. Now, the way we read it, the way we interpret the slope, we have a format here that you should probably memorize. Everything that's in parentheses is something that you would fill in the blank with, right? So if I'm going, like I said before, if I'm going to interpret the slope for this scenario so my x is my miles driven. My units for x are miles. My y is price. My y units are dollars. And my slope is negative 0.1627. So what I would say is as miles driven increases by 1 mile, price decreases by negative $0.1629. Or basically every time, another way to think about it in layman's terms, every time I drive 1 mile, the price of the car I'm driving is going to decrease by a little over 16 cents, right? Same thing when I'm interpreting the y-intercept. Again, I have my x units, my y units, and my value for my y-intercept. Same x and y from before, but now we're using the y-intercept instead of the slope. So the way I would read this, I would say when miles driven equals 0 miles, the price is $38,257. Or in other words, if I haven't driven this car yet, the price will be $38,257, or should be. Extrapolation. We can use a regression line to predict a response y hat for a specific value for a variable x, but the accuracy will depend on the strength of the regression, right? So how accurate my y hat prediction will be is going to depend a lot on that R that we talked about last time, right? Extrapolation is when you use your regression line for X for values that are outside of your range of data. So if I go up here and I say, okay, well, all of my data points are between 0 and 160,000. If I were to use my line to predict something over at 200,000, that would be extrapolating. I'm trying to find a prediction that is outside of my range of data, since my data ranges from 0 to 160,000. Extrapolation, in general, is not something we want to do. We do not want to extrapolate outside the data. The main reasoning for that is that we don't know if the model would change if we went beyond the bounds of our data, right? We know that real-life models can curve, they can follow nonlinear patterns. So if we're using a linear model to predict something that's linear, that doesn't guarantee it's going to stay linear throughout the rest of the data, right? Or throughout further points if we continued on further. And as you see, eventually, this line is going to cross this x-axis, and it's going to eventually, because of the way lines work, it's going to get below $0. If I go to buy a car and they charge me a negative price, that's not a thing. So it doesn't make sense after a certain point to use this line, which is why, in general, we don't extrapolate. So don't extrapolate. That's a no-no. Now, the least squared regression line, the LSRL. So that is the line. How is it made? The way it's made is that you take each dot and you try to essentially, well, this is not done by hand, first of all. But what is going on is a line is drawn that splits the points. And what this line is attempting to do is decrease the value of each of these squares as much as possible. So what this square represents, it's the distance, vertical distance, from each point to the line squared. So if this point is here, its distance in y units from the line is negative 4,765. And you square that value and you get 22,705,225. Now, the size of that number specifically isn't that important, but what this line does is it takes each of these points, finds the square of this residual. Residual is the name for this distance from point to line. It squares those residuals and tries to minimize the total sum of the area of each of these squares. Now, this is something that is done with technology. This is not something you're going to be asked to do by hand. Again, it's like standard deviation, but even more tedious, so it's not something that you do by hand. It's something that we do in the calculator. Speaking of, if we use the same data we had for the last slide, we have the height and the shoe sizes. Again, this was made-up data that I came up with. Remember, we had 10 data points, and we had an R value that was pretty strong, 0.95. It's about as strong as we can hope to get without totally making up unrealistic stuff, right? Well, remember I showed you how we could get a scatter plot using the calculator, and this was the scatter plot we came up with. We can also get a regression line on this calculator. The way we do it, we hit Menu, we hit Analyze, Regression, and then Show Linear. And again, this was the version that we're using for statistics. I know in algebra we used mx plus b. For statistics, we use a plus bx. And there is the line. It gives me the equation to go with it. There's my y-intercept, my a. This happens to intersect at negative 13.06 or 0.07, and then my slope is 0.3. So the way I would interpret this, I would say, for the slope anyway, I would say as height increases by 1 inch, shoe size will increase by 0.33 sizes. I don't know what the shoe size measurement was, right? I don't know how they do it in the States. I don't know what the units for shoe sizes, but we could just say the shoe size will increase by 0.33 since it doesn't. The y-intercept would say, or I'm sorry, the way we would interpret the y-intercept is that if the height is 0, the shoe size would be negative 13. Now, again, the y-intercept, if you notice, is well outside the range of the data, which is why it sounds so ridiculous. If someone is 0 inches tall, first of all, if someone's 0 inches tall, please take them to the hospital. But also, they have a negative shoe size. That doesn't really make sense. So that's another example of why we don't want to extrapolate. Even if it is included in our line, if it's not within the range of our data, we don't really want to go there. If I go back to this screen, I can run a linear regression here for my two values, height and shoe size. It might overwrite what I already had, but it gives me the A, it gives me the B, it gives me R squared and R, and it also tells me the value of each of those residuals. Now I do want to show you what happens over here. Well, yeah, I do want to show you what happens here. If I want to look at those residuals, I can hit Analyze Residuals, and I can ask it to show the residual squares. So like I said, what this is doing is it's taking each of the residual distances from the point to the line and trying to minimize it as best as it can. If I were to take one of these points and change its value, then the square would increase, but notice that the line is shifting all around to try to compensate for that point being moved, right? So it tries to keep the rest of the squares as small as possible regardless of what I do at this point. Now notice if I take it all the way down here, I get a very large residual square. This would be considered an outlier. If I move it, so it shifts my line up and down, that would obviously decrease my R. If I move it left and right, you'll see it actually changes the slope quite significantly. If I take this point and shift it over here to the right, it's very influential. So a point that is an outlier in the x direction, we refer to as an influential point, and a point that is an outlier in the y direction, we just refer to as an outlier. It changes the strength, whereas an influential point is actually going to have a significant impact on the slope. And that's all I have for you here. I hope this video was helpful.